Everything from ancient astronomical observations 2,500 years ago to black holes in space. No human endeavor has transformed society and defined our place in the cosmos more than the physical sciences. What started as a kernel of knowledge about the movement of the heavenly bodies has expanded to include the atomic building blocks of all chemistry, geology's understanding of Earth's long history and the forces that have shaped our planet's features, astronomy's picture of an ever-expanding universe populated by billions of galaxies, each containing billions of stars, and physics' understanding of the basic principles of movement, energy, and forces which have given us the technological world of cars, planes, television, computers, cell phones, and the electrification of the planet. Turning Points in the Physical Sciences takes you on an exciting journey of discovery from ancient through classical science to the world of modern physics, relativity, chaos theory, and quantum mechanics. When Italian astronomer Galileo witnessed the moons of Jupiter and the rings of Saturn, and then correctly described the most important properties of gravitation, astronomy made a giant leap into the classical era of science. In fact, astronomy was the oldest and most complete science at the beginning of the classical age of physics. Astronomy started even before recorded history, when our ancestors were confronted by a great diversity of objects and living things. Movement and change colored every aspect of their lives. The animals they hunted migrated from place to place. The day-to-day weather changed. Their bodies grew old and infirm and eventually died. But perhaps the most intriguing feature of early mankind's tumultuous life was the movement of the celestial bodies. The sun, moon, and planets crossed the sky. Day turned into night, and the year cycled through seasons. All of these astronomical events were well known to ancient cultures. In fact, ancient architects designed structures such as Stonehenge and Egyptian and Mayan pyramids to align with astronomical occurrences like the solstices and equinoxes. Then around 600 BC, a new kind of thinking emerged in Greece, the Western scientific tradition. Two fundamental concepts arose that would drive science even to the present. First, the Greeks believed that underlying the vast diversity around them was a simplicity that could be discovered by rational investigation. The second belief was that movement and change must occur according to a few basic laws. Finding what these were by free inquiry and heated debate created our scientific tradition. From this investigative milieu arose the theory that the Earth was the center of the universe, and all celestial bodies moved in perfect circles around it. This doctrine, put forth by the Greek astronomer Ptolemy in the 2nd century AD, lasted for 1,400 years. However, the problem with the Ptolemaic view of the solar system was that while producing accurate predictions from simple astronomical events such as lunar and solar eclipses, it was unable to easily account for the retrograde motion of the outer planets, Mars, Jupiter, and Saturn. From time to time, these planets appeared suddenly to change course and go back in the direction from which they had come. This problem was ignored during the Dark Ages in Europe, a nearly 800-year hiatus from astronomical inquiry and discovery. But this neglect changed at the start of the 16th century with the arrival of the European Renaissance movement. In 1512, the Polish-born astronomer Copernicus presented a more elegant explanation. He proposed a heliocentric model of the solar system, in which the planets revolved around the sun. One of the most revolutionary ideas science ever put forth. It spurred one discovery after another. In 1609, the German astronomer and mathematician Johannes Kepler showed that the planets moved in ellipses about the sun. His elliptical orbits put an end to the belief system of perfect circles. With the development of the telescope, Italian astronomer Galileo and others saw that the sun rotated every 27 days, that the moon had Earth-like features such as mountains, that Venus had phases such as our own moon, that Jupiter too had moons of its own, and that Saturn was surrounded by rings. Behind all of these discoveries was the ever-present phenomenon of movement. Everything was in motion. How did all the planets, their moons, and the sun move together in such an orderly fashion? The answer to this question began in Italy. In 1638, Galileo reported his most famous experiments. Legend states that he dropped 2 cannonballs of different weight from the Leaning Tower of Pisa. Actually, he rolled balls of different weights down an inclined plane and discovered counterintuitively they all accelerated at the same rate. He found the rate of acceleration could be expressed in a precise equation, and the force producing this result was gravity. One of the fundamental forces of nature, gravity, or the attraction between two bodies, got stronger the closer the two bodies approached each other. Hence the acceleration of falling objects. Counterbalancing gravity was inertia, the tendency of a body to resist acceleration. Heavier objects had a greater tendency to stay put. With this understanding, the foundation of classical astronomy, and indeed classical science, were now in place. "50 years after Galileo described the gravitational attraction between two objects, the English mathematician Sir Isaac Newton, building on Galileo's results, published the most important work in the physical sciences, the Mathematical Principles of Natural Philosophy, or the Principia as it came to be commonly known. In this book he explained that the force that makes apples fall to the ground and the force that controls the movement of objects in the solar system are one and the same. It is gravity. The physics that worked on Earth also held true in the heavens. In the Principia, Newton also stated his 3 laws of motion. We've all experienced that when a car suddenly stops, such as in a crash dummy test, the dummy keeps moving forward. That is Newton's first law of motion. Every object in a uniform motion tends to remain in that state of motion unless an external force is applied to it. The corollary is, if the motion is zero, the object is at rest and will stay at rest unless an external force is applied to it. It is also referred to at times as the law of inertia. Every object, such as a steel ball bearing or ping pong ball, has mass, and it takes force to get it moving. This sluggishness is called inertia. Shake both balls in your hand and you can feel it takes more effort to get the steel ball going than the ping pong ball. The steel ball has greater inertia, therefore a greater mass. Everyone instinctively knows the second law, that heavier objects require more force to move them the same distance than do lighter objects. It is easier to push a bike than a car. The second law gives us an exact expression of this intuitive understanding. It is the relationship between force, mass, and acceleration. Rather than maintaining a constant velocity, force produces a change in velocity. In other words, acceleration. The relationship is expressed by the equation force equals mass times acceleration. Most people have also experienced Newton's third law of motion. When a person jumps off a skateboard and the board is propelled along the sidewalk, it is Newton's third law of motion in action. The third law states, for every action, there is an opposite and equal reaction. With these laws and a new mathematical procedure for computing acceleration called calculus, invented independently by Newton and the German mathematician Wilhelm Leibniz, the motions of the bodies in the solar system fell to the computations of Newton's celestial mechanics. Validating the power of Newton's mechanics came with predicting the return of comets, particularly the prediction of the return of the great comet of 1682. In 1705, English astronomer Edmund Halley wrote, "I dare venture to foretell it will return in the year 1758. And so it did, and has been known as Halley's Comet ever since. Further validation occurred when Sir William Herschel, using Newton's principles, discovered Uranus, the seventh planet in the solar system, in 1781. These historical observations laid the groundwork for Pierre Laplace's theory on the origination of the solar system. In a popular book on astronomy, Laplace suggested the sun came from a rotating giant nebula, or a cloud of gas. As the gas contracted into our sun, the rotation of the gas cloud left behind rings of gases that eventually condensed into the planets. Laplace's theory has withstood the test of time, and with it closed the final chapter of ancient astronomy. In the next 200 years, astronomers trained more efficient and larger telescopes beyond the solar system for even more startling discoveries into and about the universe. Electricity and simple water would come together in two experiments performed in 1800 that would lead to the greatest advance in technology the world would ever see, meaning ember. Electricity was first used by the Greeks to describe the static electrical sparks produced when amber and fir were rubbed together. By the 18th century, the strange phenomenon of static electricity was a major focal point of scientific investigation. Using the same principles in achieving a spark from amber and fir, experimenters built electric machines like the one seen here. These machines readily produced electrical charges that could be sparked or stored in Leyden jars. The popping and crackling sound of the electrical sparks produced by these machines reminded 18th century scientists of the thunder associated with lightning. In fact, in 1750, American Benjamin Franklin demonstrated by his famous kite experiment that lightning and electricity were one and the same, a remarkable achievement for the time. But the quick discharge of static electricity made it difficult to study. That changed in a dramatic sequence of observations from 1786 to 1800. First, Italian Luigi Galvanic made the chance observation that a charge from an electric machine could make the leg of a dead frog contract. He went on to show that connecting two dissimilar metals could produce the same contraction. He called this phenomenon animal electricity. Next, another Italian, Volta, made one of the great intuitive deductions in science. He reasoned it was not the animal that was producing the electricity, but the arrangement of metals and moisture. In 1800, he built the voltaic pile. In short, he built the first battery. He put together a little pile of discs, sequencing silver, zinc, and wet paper. On the top was zinc, and the bottom silver. By connecting wires to the top and bottom of his pile, he produced the first electrical flow, the first man-made electric current. In the same year, hearing of Volta's invention, William Nicholson, an English chemist, built his own primitive battery and immersed the two leads into water. Bubbles of gas rose to the surface. What was going on? By this means, later called electrolysis, Nicholson had actually decomposed water into its atomic components, hydrogen and oxygen. Oxygen appeared at one pole of the stack, the positive, and hydrogen at the other, the negative. Nicholson was in fact the first to perform electrolysis and the first to demonstrate that an electric current could produce a chemical reaction. From that moment, while still a mysterious phenomenon, electricity as a current would go on to power all the technological advances of the modern world. As for electrolysis itself, it would be used to separate many chemicals into their constituent parts. In the 20th century, the greatest technological impact of electrolysis would come in the form of the final step in the extraction of aluminum from bauxite ore. Ironically, 200 years after the first experiment in electrochemistry, the reverse process, the joining of hydrogen and oxygen to form water, is the greatest hope for a new form of clean energy. It's called the fuel cell. Fire, earth, air, water. From the time of the Greeks and Aristotle, natural philosophers believed that all things were made up of four basic elements: earth, fire, air, and water. It was called the phlogiston theory of matter. It was a limiting belief held until the mid-17th century, when Robert Boyle, often called the founder of modern chemistry, began to question its validity. What drove the chemists, or some would say the alchemists, for hundreds of years was the search for the philosopher's stone, a mysterious substance that supposedly turned base elements into gold, cured all disease, restored youth, and granted immortality. While not abandoning the alchemists' search to transmute metals, Boyle challenged the long-held assumption that every substance had to contain at least a small amount of the phlogiston's theory's four basic elements. He did this in the publication, The Skeptical Chemist. In publicly presenting his experiments, he broke with the tradition of secrecy maintained by the alchemists. This dramatic shift began the open exchange of ideas in science, the hallmark and even ethic of modern science. A century later, the scientific method, experimentation, observation, and publication, had supplanted the clandestine tinkering of the alchemist. As a result, the 18th century became the heyday of using heat to produce chemical reactions, as well as the study of gases. Particularly under assault were two of the phlogiston's theories' basic elements, fire and water. What were they really? The idea of water as a primary element was so strongly embedded in people's minds that many people thought it heretical when scientists demonstrated it was merely a false assumption. Water cannot be an element if it is made up of something else. By 1784, chemists such as Joseph Priestley, Antoine Lavoisier, and Henry Cavendish had shown in a series of experiments and demonstrations that water was, in fact, not a fundamental element. Water was actually made up of oxygen and hydrogen. Not only had they separated water into oxygen and hydrogen, but they also reversed the process using oxygen and hydrogen to produce water. In one such ingenious experiment, Priestley used a magnifying lens to heat mercuric oxide, which gave off pure oxygen. He trapped it in the glass container that housed the experiment. Now, with ample oxygen to play with, Priestley and others quickly learned that this gas could enhance the burning of a candle and other combustions. The old phlogiston theory was collapsing, but what would replace it? By the turn of the century, electrolysis of water had allowed scientists to simultaneously capture both hydrogen and oxygen. One of the intriguing questions that resulted from these experiments was, why was there always twice as much hydrogen as oxygen? And why was carbon dioxide, another gas given off by fermentation, always made up of the same proportions of carbon and oxygen? The answer came in 1808 when John Dalton published his new system of chemical philosophy. In it, he proposed that matter was made of atoms, tiny invisible spherical bodies of fixed masses. Some of his elements were hydrogen, carbon, sulfur, iron, silver, and gold. But unlike earlier atomists, he assigned a specific weight to each of his elements. This was the conceptual revolution all chemistry was waiting for, and would lead to the periodic table 60 years later. Although some of Dalton's elements were in fact compounds and his nomenclature was never accepted, this new idea of matter spread like wildfire. The atomic nature of matter set the stage for all the great discoveries of the 20th century, and eventually to the release of energy from the atom itself. Of all the phenomena that would eventually comprise modern physics, light was the most enigmatic to ancient cultures. Undoubtedly, they pondered over the sun's effect on the earth and the formation of rainbows after violent storms. Light's power was even harnessed to some extent in the 3rd century BC when the famous Greek engineer and inventor Archimedes designed colossal mirrors which set fire to a Roman fleet attacking Syracuse. But it took until the second half of the 17th century for the serious study of light to begin. In 1672, Sir Isaac Newton published the results of a series of experiments on light. He had recreated the rainbow in his lab using a prism, and in doing so demonstrated that light was actually made up of component colors: red, orange, yellow, green, blue, and violet. This dispersion of light, or refraction as it is sometimes called, occurs when light moves from a less dense medium such as air to a denser medium such as glass. This changes the wave speed and is described as the refraction index. Then in 1675, using eclipses of Jupiter's moons as the planet moved closer or further from the Earth, Danish astronomer Ole Romer came up with a close approximation for the speed of light. It was traveling at the incredible rate of 186,000 miles per second. Still, fundamental questions remained. What was the nature of light, and what was it that was traveling at such a remarkable speed? Newton argued that light was a stream of tiny particles, or corpuscles, as he called them. However, his rival, the Dutch astronomer and physicist Christian Huygens, challenged the corpuscular theory and claimed that light traveled on waves through an invisible medium called ether. Newton's corpuscular theory of light dominated the thinking of scientists for the next century until the early 1800s, when a young Englishman, Thomas Young, made a startling discovery. He knew that if 2 pebbles are thrown into a quiet pond, waves radiate from the center of each impact. When the waves reach each other, a new pattern is formed, as the waves either cancel or strengthen each other. This new pattern is called an interference pattern, and all waves produce it when they come in contact with each other. So Young designed a simple experiment to test the nature of light. He shined light through 2 tiny pinholes in a piece of cardboard. On the other side was a screen. What showed up on the screen was an interference pattern with dark areas where waves were obviously canceling each other. Light was clearly behaving like a wave. What followed was an explanation for the component colors of light. They were different wavelengths, red being the longest and violet the shortest. Building on this discovery a half-century later, James Maxwell formulated his famous theory of electromagnetic radiation. The next step in the study of light came in 1814 when a German lens maker built the first crude spectroscope. Rather than view the colors produced by a prism with the naked eye, Joseph von Fraunhofer used a telescope in his laboratory. What he saw through his telescope was a surprising number of black lines scattered throughout the color spectrum. Fraunhofer labeled the major divisions from A to K. These dark areas are still called Fraunhofer lines today. In fact, the dark lines were wavelengths absorbed by atoms, and the colors were wavelengths radiated by the same atoms. In the 1860s, improved spectroscopes revealed an incredible find. Each element had its own distinctive pattern of lines and colors. By heating elements so they would give off light, each produced a unique fingerprint that could be recorded and used in the analysis of chemicals, the sun, and other stars. Spectral analysis would greatly aid in the discovery of new elements such as helium in the sun. By the end of the 19th century, the debate over the nature of light would be revisited, resulting in the greatest paradox of the physical sciences, that light was both a wave and particle.